In part 2 of section 22, we're going to be looking at something called a recursion formula. Definition 22.2 gives us a little more insight into this idea of recursion. What we're defining here is a recursive sequence. A recursive sequence defines the nth term of a sequence as a function of a previous term. So this is vastly different than what we were seeing in any of the previous examples that we saw. So, for example, on the previous example, 22.2, one of the sequences we were working with was an equals 2n plus 5. And we calculated a1, a2, a3, and a4. If I wanted to, I could very easily calculate a50 just by simply taking 50 and plugging it in. I would get that a50 is equal to 105. I don't have to know anything about the 49th term in order to figure out what the 50th term is, because I can just directly substitute in 50. In a recursive sequence, you cannot just jump around in the sequence. You have to find the terms in order, because it is a function of a previous term. Example 22.3 is going to help to illustrate my point with that, as this is going to be a little bit of a contrast from the previous sequences we saw. Now the instruction starts very similar. It says find the first 4 terms of the sequence. Find the first 4 terms. We know what that means. In which a1 is equal to 3, an is equal to 2 times a with a subscript of n minus 1 plus 5, and then it continues for n greater than or equal to 2. So both of these pieces that I've underlined together represent the sequence definition. All of that together is your sequence definition. And the nice thing about this style of sequence definition, which again is called a recursive sequence or a recursion formula, is that they actually give you the first term for free. And I don't know about you, but I like free stuff. a1 is equal to 3. Now the others we're going to have to work for, but we know what to do to calculate a2. a2 means plug in 2. So if I plug in 2 into this recursion formula, it's going to be 2 times a with a subscript of 2 minus 1, and then I'm going to tack on that plus 5 there. So this is the first time that we've ever substituted into an equation or a formula where we're plugging into the subscript. So we're going to have to talk a little bit more about what this means. So what's going to happen in terms of simplifying this is I'm going to start with that subscript, and I'm going to simplify the subscript so that way it just has a 1 down there, since 2 minus 1 would be 1. So what this is claiming is that I have to take the a1 term, multiply it by 2, and then add 5. So the answer that I had from a1, which was provided, was 3. So if I multiply 2 times 3 and then add 5, I get a total of 11. So there's no way that I could possibly calculate the value of 11 without using 3 from the previous term. This is what makes it recursive compared with a other type of sequence that we saw on the other examples. So let's take a look at calculating a3. a3, if I simply just plug in 3 into the formula, it's going to say 2 times a with a subscript of 3 minus 1 plus 5. Simplifying the subscript makes the subscript now say 2. So this is implying that the only way that I can calculate A3 is if I have knowledge of A2. So this is going to say 2 times 11, because that's the previous answer for A2, and then add 5 to that. So 2 times 11 plus 5 gives a total of 27. And we'll do this one more time since we are asked to find the first 4 terms. A4, 2 times A with the subscript 4 minus 1 plus 5 is going to give us A3. So the only way for us to calculate A4 is if we have previous knowledge of A3, which we've already done. So we're going to take A3, multiply it by 2, so that's going to be 2 times 27, and then add 5 for a grand total of 59. Listing all the terms, 3, 11, 27, 59, and that would be our final box and answer for finding the first 4 terms of this sequence.